watching that video of walking into my office that I haven't physically walked into for about the last 2.5 weeks or so. Good afternoon to everyone out there in pre-calculus and trigonometry land. We're going to do our second session of the week this week and use the time to wrap up a couple of topics that we didn't get to in our previous session. So I do want to do a little bit of talking about logarithms, how we can use logs to solve equations, how we can use the properties of logarithms to simplify expressions, just as a way of kind of exposing ourselves to some more problem solving in those areas. And then I want to shift and talk more about trigonometry, take kind of a flyover of all the trigonometry topics we've talked about up until this point, talk about some trigonometric graphs, periodic function graph phenomena, use the right triangle definition of some trigonometric functions to do some problem solving again, and then also get some additional exposure to what inverse trigonometric functions are and how they work. So that's the agenda for our session together today. If you're taking my class this semester, be on the lookout over the next 24 hours or so for me to post the first of our trigonometry quizzes for the semester. There are currently quizzes on the exponential and logarithmic function content that are available, quizzes 4, 5, and 6. Those you should continue to work on throughout the week. They're due at the end of the day, 11:59 p.m. on Sunday this weekend. So let's just jump right in head first today and talk about how we can use logarithms to help us in the process of solving exponential equations. So again, like Monday, a lot of the examples I'm going to talk about today came from Kathy Yoshiwara's great college algebra book called Modeling Functions and Graphs. So I'm going to borrow some of the problems from there. We'll talk about how to use logs to solve equations, how we can use logarithms and the properties of logarithms to simplify logarithmic expressions, and then from there we'll shift gears and we'll talk about some trigonometry stuff. So, how do we solve equations where the variables that we're trying to solve for are trapped up in the exponents? That's the big question that logarithms seem perfectly suited, perfectly tailored to help us to answer. So depending on how the problem is set up, sometimes this can be quite simple, and sometimes there can be a bit more work to do. So the problems that we see here on the screen, those are set up so that they're going to require us to do a little bit of work, but maybe it's not as bad as we think. I actually want to start with this last problem, problem 24, over here on the side. In this problem, the left-hand side of the equation, 3 to the power x squared minus 4, that left-hand side is written as though it is a power of 3, right? It's 3 raised to some power. And the right-hand side of this equation, 27, that also, if you think about it, is itself a power of 3. In fact, it's a power of 3 that's relatively simple for us to think about off the top of our head. After all, how many times do we have to multiply 3 by itself in order to get 27? Well, 3 multiplied by itself once, 3, just plain 3 is 3. Right? 3 times 3, that's going to give me 9. But if I multiply one more time, 3 times 3 times 3, that's going to give me 27. And so the simplest way to be able to solve a problem where we have our variable trapped in the exponent is, if we can, let's try and write both sides of this equation as a power of the same base. So the left-hand side is already written as a power of 3, 3 to the power x squared minus 4. But once we recognize that 27 is also a power of 3, namely it's 3 to the power 3, what that does for me is it allows me to then undo that exponentiation that's happening on both sides of this equation all in one shot. And we won't need to do anything quite so dramatic as use logarithms. So what I want to do is show one way of solving this equation without explicitly using logarithms. And then I also want to do it a second time explicitly using logarithms. And so I'd like for us to be able to compare those two approaches. All 4 of the problems that are on the screen here can be done either way. We don't have to explicitly bring out the log stick to hit these problems with. We can, and it will work every time. But there's an alternative approach, and I think this alternative approach also helps us to understand what logs are in the first place. So that's why I like doing them both. All right, enough of me talking about doing it. Let's actually just do it together and see how it works. So as you might expect, if I have both sides of my equation that are powers of 3, then since every exponential is a one-to-one function, every exponential function's graph passes the horizontal line test. And for that reason, I'm just going to kind of write that in the margin here. Every exponential function is one-to-one. It's invertible. Passes the horizontal line test. It passes the vertical line test because it's a function, but it also passes the horizontal line test because every exponential function, as long as its base is not equal to 1, we can talk about that some other time, every exponential function passes the horizontal line test, and so it's invertible, which means if I put two different inputs into an exponential function, I get two different outputs at the end of the day. And so if I end up getting two of the same output from an exponential function, that must mean that both of the inputs themselves must also have been the same. How does that help me in this equation right here? Well, both left and right-hand sides we can think of as outputs from the function f of x equals 3 to the x, or f of t equals 3 to the t, whatever, 3 raised to the power. Both of these are outputs from that function. One of them is an output with an input of x squared minus 4. The other one is the output with an input of 3. But because every exponential function passes the horizontal line test, if I put both x squared minus 4 and 3 into an exponential function and I get the same output, equal sign, right, that must mean that the inputs were the same. And all of that is a long-winded way to get to what you were probably hoping that we could get to, which is just, we can forget about the exponentiation completely and just set the exponents on both sides of this equation equal to one another. And that has the effect of rescuing my variable that I'm trying to solve for. My x has been rescued out of the exponent and is now down on the floor where we can finish the process of solving for it, right? So that's the magic of having both sides of the equation written as an exponential expression using the same base. We can just forget about the base and equate the two exponents. And the algebra from here is familiar algebra. Add 4 to both sides to get x squared equals 7. And then simply take a square root on both sides. When I take the square root of 7, I get some funny irrational number, something between 2 and 3, probably a little closer to 2 than it is to 3. 2.5. No, it's actually a little closer to 3. Let me turn off my email notification. I don't like hearing my email notification on good days, but especially not when I'm trying to teach. So on the right-hand side of this equation, we have the square root of 7. But on the left-hand side, we have the square root of x squared, which, remember, is not equal to x, because my exponent is even. It's equal to the absolute value of x. And it's in getting rid of that absolute value in solving for x. That's where we end up with this plus or minus sign on the other side of the equation. So x equals plus or minus the square root of 7. So there is a way of solving this equation without explicitly making reference to logarithms. But if we wanted to make explicit reference to logarithms, we could do that too. So let's try it. So here's the alternative way of doing this, where we're going to be more explicit about the fact that logarithms are the tool that we can use to rescue a variable from out of the exponent. So I'm just going to rewrite the problem here again. 3 raised to the power x squared minus 4 is equal to 27. So if I want to rescue something out of an exponent, all we have to do here is remember, I'm going to bring up what is my favorite visual for all of this. Remember the definition of logarithm, how to rewrite an exponential equation as a logarithmic equation instead, or vice versa. So let me bring my favorite visual back up on the screen here. I'm sure you know the one by now. Here we are. Right? Every exponential equation we can rewrite as a logarithmic equation. All I have to do is trade places between what you see here as the x and what you see here as the y. Trade places between the input and the output of this exponential function. After all, trading places with input and output is how we define an inverse function in the first place. So if I want to change my exponential function here into exponential equation rather, into a logarithmic equation, what I ought to do, why don't we just replace b by 3, because that happens to be the base that we're looking at in the problem that we're trying to solve now, right? Upstairs we have something complicated, x squared minus 4. But then my right-hand side, in place of the y, we have a 27. So let's change that to, so in place of y, we've got 27. And so now, as you might expect, if we trade places between the exponent, the x, and the power, 27, then that exponentiation by 3 turns into a logarithm with a base of 3, right? After all, if 3 raised to some power is equal to 27, then that power, that exponent, that x, is by definition the base 3 log of 27. It's an answer to the question, how many powers of 3 does it take to make 27? Right? So we're just going to do that. Just in place of x up here in the exponent, we'll have the exponent that we're actually interested in, which is x squared minus 4. So when I trade places between the x squared minus 4 and the 27, I'm reversing the roles of the input and the output of the exponential function f of t equals 3 to the power t. And so on the left-hand side, I'm going to have not the exponential function, but its inverse, which we call the base 3 logarithm. X squared minus 4 ends up on the right-hand side, and 27 then ends up as the argument of my base 3 logarithm function. Log base 3 of 27. Right? And so from here, we have a couple of different options. If we want to just evaluate the base 3 log of 27, all we have to do is do the sort of kind of backwards thinking that it takes to use the definition of logarithm. It's an answer to the question, how many powers of 3 does it take to make 27? Which was actually kind of the first thing that we did when we were solving the problem the other way, right? The first thing I did here is say, well, 27 is really just 3 powers of 3. Right? And that same reasoning is why the base 3 log of 27 is equal to 3. So that's a way of doing this without resorting to scary logarithms or calculators or what have you, right? But let's suppose that either we didn't feel like being clever enough to do that backwards thinking to figure out the base 3 log of 27, or maybe there's a lot of logarithms out there that we can't just do using mental arithmetic. So what would be our other way out? How else could we have gotten that base 3 log of 27? Well, here's the magic of the change of base formula once again. Right? The base 3 log of 27 using the change of base, COB, we can rewrite as the log of 27 divided by the log of 3. And those logs, right above my head here, those logs can be taken with respect to any base that we like. Okay? That's the real beauty of the change of base formula. So let's suppose that we want to use a base 10 log. Generally, when we're applying the change of base formula, it's because we want to use a calculator to be able to evaluate this logarithm. And calculators generally only have 2 types of logarithms that they can do. A base 10 log, which is called LOG on a calculator, or a base E log, which is called a natural logarithm, or LN. Right? So for the base 10 log, let's just do that one this time. I'll just take 27, compute the base 10 log of it. I get a number, something like 1.43. I'll divide that by the base 10 log of 3. And sure enough, my calculator at the end of the day gives me the same answer, 3, that we got when we just were thinking about what the base 10 log, what the base 3 log of 27 was. So you do out all that work, the calculator tells you that that answer is 3. So whichever way you slice it, we're ending up in exactly the same spot here as we were there, and then we would just continue along with the same steps to finish solving the equation as we had in the first place. So what about one of these other examples? What makes them different or maybe potentially a little bit more challenging? Well, one thing that we could think about, let's look at problem 23. So it's the one right above my head here. I'm going to just clear a little bit of space so that we have some room to write. There we go. So if I were to do problem 23, what you immediately notice, or at least what I immediately notice, is that both sides of this equation are written as exponentials, yes, but they're not written as exponentials with the same base. Having exponentials with the same base was a huge advantage in solving this first equation. But if the bases aren't the same, then we might have to do a little bit more work. So once again, let's look at a way of doing this using logarithms, and then let's look at a way of doing this without using logarithms. And this time, I think I want to do the hard way, the logarithm way, first. So logarithms are a tool we can use any time that we want to rescue something out of an exponent. And in this example, both sides have an x as part of the exponent. And so we need to be able to rescue both sides' exponents from out of the exponents. So why don't we just take a very naive approach and just hit this thing with a log? Maybe just for fun, I'm going to use a natural log this time. In other words, it's a logarithm with a base of e. Right? So I'm just going to take the logarithm of both sides. Logarithm on the left, logarithm on the right. Over here, it's the logarithm of 4 to the power 2x plus 1. And on the right, it's a logarithm of 8 to the power x minus 3. Well, okay, great. How does taking a logarithm on both sides actually help? It almost looks like it's made things more complicated rather than less complicated. So let's talk about that piece. If I can find my logarithm, I don't know where that went here. Sorry, just give me one brief second here. I'll be right back. Sorry about that. So what gets us out of the bind here is any logarithm that we could write down enjoys the properties that apply to all logarithms that we're going to talk about sort of next. So we're going to go more in depth into these in just a moment. But the property that's going to help us here is the property that says that a logarithm of a power is equal to a multiple of the logarithm. In other words, when I take the log of something that is itself an exponential expression, I can take the exponent of that expression and bring it out and multiply in the front of the logarithm instead. So that's what ends up getting us rescued in this example. Whoops, sorry. So what that looks like is I'm just going to take my exponent in both of these expressions, and I'm just going to rewrite it as a multiple in front of the logarithm. That has two benefits. The first is that it brings my variables, my x's, these expressions that have my unknown in them, it brings them out of the exponent and down onto the floor where I can finish solving for them. And, excuse me, it also has the wonderful property that what's left inside of each of the logarithms is just a number, a constant. So in the first example, on the left-hand side, I'm going to get 2x plus 1 times the natural logarithm of 4. Right? And then on the right-hand side, I'm going to get x minus 3 times the natural logarithm of 8. And now my x's are all down on the floor where I can solve for them. and we should be able to sort of continue from here. What I'll do, just because my head's kind of in the way, I'm going to continue up at the top of this next line. So what I actually want to do here is I want to get all of my variables onto one side and all of my logarithms onto the other. So what I'm going to do actually is divide both sides by the natural log of 4, and then also divide both sides by the quantity x minus 3. So I'm actually going to open this in my fun, graspable math palette over here. So what do I have here? 2x plus 1 times the natural log of 4 equals x minus 3 times the natural log of 8. All right, so let's do the equation gymnastics to rearrange this thing and try and get that x by itself to the extent that we can. So I'll move over into, here we go, sorry, scoot this over just a little bit. All right, so here we are. I want to get that x by itself. So remember, natural log of 4, it doesn't really look like it's a number because it has that ln in front of it, right? It looks like it's a function. Well, natural log is a function, but when we feed a function whose domain is the real numbers, a real number, and whose range is a real number, natural log of 4 is just a real number. If you plug it into a calculator, it's something between 1 and 2, closer to 1 than it is to 2. So I can just divide both sides of this equation by that number, natural log of 4. And then in the same way, I can divide both sides of my equation by the quantity x minus 3. Let's bring that over here. And so what I have now is an equation that has the variable that I'm trying to solve for, x, just on the left-hand side, and the right-hand side of my equation, log 8 over log 4, those are just numbers. And so this is a time when I could pull out my calculator, do natural log of 8 divided by natural log of 4, and then we could be done, right? But if you do that, you find out that you actually get a pretty nice number out the end of that process. So I want to take this as an opportunity to use the properties of logarithms to figure out why that might be the case. So one of the ways that we could understand the natural log of 8 divided by the natural log of 4 might be to think about what 8 and 4 have in common. On the one hand, we could write, we could do it the way a calculator does it, which natural log of 8 is some nasty decimal, natural log of 4, some nasty decimal. But when we divide the former nasty decimal by the latter nasty decimal, we end up getting a pretty nice decimal, 1.5, or if you like, 3/2, right? If I undo those steps. What's another way to understand why this might be 3/2? Well, let's go back to to my whiteboard for just a second. 8 and 4 have something in common. Namely, both of them are relatively simple powers of the same base. Namely, both of them are powers of 2. 4 is 2 to the second power, and 8 is 2 to the third power. So one other way of understanding why this quotient is what I'm claiming that it is to think of it in that way, right? Think of them as natural logs of something that has the same base. So one way of doing that, I'm going to again get my fancy math palette over here. Think of it as a natural log of 2 to the third power divided by the natural log of 2 to the second power. And if I think of it that way, I can again use that same property of logarithms that says that the logarithm of a power is the same as a multiple of that logarithm. So that exponent can be brought out into the front. But notice what happens when I do that. I end up with a fraction that has a common factor of natural log of 2, both in its numerator and its denominator. And for that reason, those natural logs of 2 can just cancel. And so that's why this ratio ends up being 3/2, right? If we sort of recognize that both 8 and 4 are powers of the same base, 2, then when we bring those exponents out using the properties of logarithms, the leftover logs of 2 just cancel. So this is the tack that I might recommend taking. And this is a tack that helps us to sort of remember how the properties of logarithms are actually useful for us in solving an equation like this one. So I end up with something like 2x plus 1 over x minus 3 equals 3/2. And from there, we could take a number of different approaches for this, but probably the one that I would favor is crisscross the railroad tracks, applesauce, yada yada, whatever. When two fractions are equal, their cross ratios are equal. And so I get something like 2 times the quantity 2x plus 1 equals 3 times the quantity x minus 3. And from here, this is just a straightforward linear equation of the type that we've solved a lot in our lifetimes, right? I'll subtract 3x from both sides. I'll subtract 2 from both sides. I get x equals negative 11. And that's that. Sort of dust off our hands and be done. So this is a way of doing this equation, solving this equation, using logarithms and the properties of logarithms. But the same sleight of hand that we did here, that same realization that really 4 and 8 are both powers of the same base, we can use that much earlier in the process than we used it here, right? I started this problem just by hitting both sides of the equation with a log, and that will always work. As long as you have your wits about you and you remember properties of logarithms, you can always get from there to the finish line. The clever way of doing this, though, is to try and use this observation up front. Right? Both 4 and 8 are powers of 2, and for that reason, we can rewrite both sides of this original equation in terms of the same base, 2. So let's use that right now. So 4 was 2 to the power 2. So I'll just replace that 4 by 2 to the power 2. I'll replace the 8 that's on the right-hand side with 2 to the power 3. And then we end up getting something that would look like this. I'm going to be real careful with parentheses. So 4 to the power 2x plus 1, 2x plus 1, is equal to 8 to the power x minus 3, right? I think we can all agree on what was done here. 4 was replaced by 2 squared, 8 was replaced by 2 cubed. But the benefit of this is now both sides are powers of powers. And when you take a power of a power, what do you do to the exponents? You multiply them. Which, by the way, is exactly the exponential version of the property of logarithms that we had to use previously, the property that said that the log of a power is a multiple of the logs, for exactly the same reason that a power of a power multiplies the exponents. Okay. So very same property, just used in a slightly novel way, right? Used at the level of exponentials instead of used at the level of logarithms. So once we use it that way, all we have to do is multiply those exponents on both sides, right? And once I've multiplied exponents on both sides, what I end up with in this example is 2 to the power 2 times 2x plus 1. And on the right-hand side, 2 to the power 3 times the quantity x minus 3. And what you notice is that this looks an awful lot like that. Right? And that's not an accident, because what can we do now? We can do the same thing that we did in the very first example, because both sides of this equation are now powers of the same base, and every exponential function is 1 to 1. It passes the horizontal line test. We can just equate the two exponents, and then we don't have to worry about this being an exponent problem at all anymore. 2 times 2x plus 1 equals 3 times x minus 3, and then we are right back where we were there. Right? So one of the things that you notice about problems like this is that there's a way to do it that's sort of brute force. You just hit it with a logarithm, and then you use the properties of logarithms to get home from there. But that is not the only way to approach these problems a lot of the time. A lot of the time there is one of these more elegant approaches where let's try and rewrite both sides of this equation using the same base. And if we can succeed in doing that, then all we have to do is forget about those bases at all and just equate the exponents. So we saw in these last couple of problems how the properties of logs really help to bail us out. Let's dwell just a little bit longer on properties of logarithms so that we can use them to simplify some more sort of different types of expressions. So when we first introduced the properties of logs, we said that they sort of came in these 4 different flavors. And they came in 4 different flavors because these are exactly equivalent to the 4 different properties that exponents have. Right? We have one property that explains how to add exponents, or how and when to add exponents. We have a property that tells us how and when to subtract exponents. And then we have a property that tells us how and when to multiply exponents. And then we had this 4th property called the change of base formula that helped us to transform a logarithm in one base in terms of logarithm of another base. So let's see how these types of properties can be useful in helping us to simplify some logarithmic expressions. So what I want to do is I want to pick on a couple more problems out of Yoshiwara's college algebra text, modeling functions and graphs, just to give us some additional practice with this. So I think the one that I want most to talk about, let's look here at number 54. So in problem 54, I'm going to zoom in on it for us a little bit. In this problem, we've got kind of a nasty looking logarithmic expression to try and simplify. And it's a base 10 log of the square root of a product of a couple of factors. And in that product, my factors have some subtraction going on inside of them, right? I have a minus sign inside each of the factors. And then one of my factors also has that power of 2 on it. So s minus a times the quantity s minus g to the power 2. And so our task is to try and rewrite this thing using the properties of logarithms and exponents. So the first thing I would recommend doing anytime you see a square root, by the way, this is a property that is going to help you in your calculus class immensely. Always, anytime you are trying to do algebra and especially calculus with radicals, replace those radicals with powers. And in the case of a square root, remember, the square root of a number is the same thing as that number raised to the power 1/2. So anytime you see a radical, before you do any complicated algebra or for sure calculus with it, replace it with a power, because powers are something that we generally have a much better dictionary of rules for how to simplify. So that'll be the first thing that I do here. I'm just going to rewrite this as the base 10 log of, and then I'm going to write the stuff that's underneath the radical, s minus a times s minus g to the power 2, and then that whole quantity underneath the radical here is being raised to the 1/2 power. So I've just taken and rethought of that square root sign as being a 1/2 power instead. Okay. Whoops, I'm off the screen just a little bit, ever so slightly. Let me nudge myself over to make sure that we're not missing anything. All right, sorry about that. Cool. So we replaced the square root with a 1/2 power. Now, what is the benefit in this example of that replacement? Remember, this whole thing is an argument to my base 10 logarithm function. How does that help? Well, that helps because of, again, the properties of logarithms. And in this example, the property that makes the difference is this one right here. The logarithm of a power is the same thing as a logarithm of the base multiplied by the exponent of that power. Right? We can take the exponent and bring it outside as a factor in front of the log. And so in this example, the exponent that we can bring out is this exponent of 1/2. I'm being super careful with the order of operations here, right? This whole expression on the inside is being raised to the 1/2 power, so that's why the 1/2 can be brought out. I can't bring out this 2 right now, because the whole expression here is not being raised to the 2nd power, but only this factor of s minus g is being raised to the 2nd power. So be super careful with order of operations, as usual. So we'll take this 1/2, and using the properties of logarithms, we can bring that 1/2 out in front of the log as a factor. So we'll have here 1/2 times the base 10 log of, and then I have a product on the inside, s minus a times s minus g squared. Again, remembering that that square on my s minus g is applying just to the s minus g factor. All right, so far so good. So what happens next? again, thinking about sort of the outside in, this second power, according to the order of operations, applies to the s minus g. And this multiplication then connects the s minus g squared with the factor of s minus a that's next to it. And so it's actually this multiplication that I can deal with next. Because now I'm looking at the base 10 logarithm of a product of two things. And we have a logarithm property for that as well. It comes from the same property as the product of powers property. Remember that when I multiply two powers that have the same base, that's the same thing as, whoops, not that. That's the same thing as adding the exponents. And for that same reason, when I take the logarithm of a product, it's the same as the sum of the logarithms, right? Exponentiation turns a sum into a product, and for that same reason, logarithms turn a product into a sum. Because after all, the two are inverse functions to one another. So that multiplication that's happening on the inside of my log turns into addition happening on the outside. And so I'm still going to have my 1/2 that's out in front of everything here. And now again, I'm going to use parentheses to be super careful. That 1/2 is now going to be multiplying the sum of the base 10 log of s minus a and the base 10 log of s minus g squared. And I'll put that s minus g squared inside some parentheses here too. Okay, so it seems like we're getting closer. There's only one thing left that I would want to do. And that's, once again, to look for more places to use these properties of exponents and logarithms. And the one place that I'm finding that I can still use properties of logs is right here. I have a power inside of this base 10 logarithm. It's the log of the second power of s minus g. And so, once again, that power inside of the logarithm can become a multiple on the outside of the logarithm for the same reason that a power is equal to a power of using the same base but with a product of the exponents, right? Exponentiation turns multiplication into exponentiation, and so logarithms turn exponentiation into multiplication because those functions are inverse to one another. So the moral of that story is I can take this second power and bring it out in front of its logarithm, and then we will have a fully simplified logarithmic expression. 1/2 times the base 10 log of s minus a plus 2 times the base 10 log of s minus g. Done. This is an appropriate place to also caution that there is in fact nothing that we can do inside of a logarithmic function with addition or subtraction, right? Addition or subtraction inside of a log doesn't do anything. Addition or subtraction inside of an exponential expression does do something. And so this is where people sometimes get turned around, right? Because addition inside of an exponent, such as in, whoops, I screwed that up again. Addition inside of an exponent, such as in a to the power n plus m up there, right? Addition of exponents is the same thing as a product of those powers. But addition inside of a logarithm is not the same thing as anything. So there's nothing that I can do to make this logarithm any simpler or to make that logarithm any simpler. And that's how we know that we're done simplifying in a question like this one. So this was kind of an example for us to use a variety of different properties of logarithms. We can do more examples later on, going into next week if people are really interested in that. But for now, I think it's a good time to close the book on exponents and logs for now, so that we have a chance to talk about some trigonometry and some of the more triggy stuff that we have on our plate. Let me just use this as an opportunity to pause real quick and see if those of you who are watching have any questions or anything you particularly want to see addressed in the course of our last 20 minutes here as we dig into trigonometry. Cool. All right, so let's move on and let's talk trig for a little bit. So the first thing, before we get to trigonometry proper, I kind of want to use our first problem. Maybe we'll make it into two problems. I want to use it as an opportunity both to think about periodic functions in some generality, and then also to think specifically about the periodic functions that we've been most acquainted with, namely the trigonometric functions, sine, cosine, and maybe tangent, but I'm not sure if we're going to get to tangent today because I'm kind of more interested in dwelling on sine and cosine. So remember, first of all, what a periodic function is. A periodic function is a function that repeats itself at regular intervals of its inputs. So here is a graph of a periodic function. So it's kind of doing the exact same thing on one interval of its input as it does on the next interval of the same width, as it does on the next interval of the same width, and so on and so on and so on. So one way of operationalizing this using function notation might be to say something like, well, first of all, what is the period? What does it look like the period is of this graph? A period is nothing more than the difference in input values in between values that always correspond one to another, how long it takes the function to repeat itself. And at least on the graph that we're looking at on the screen right here, this again is coming out of Yoshiwara's Functions Modeling and Graphs text, it looks like this is repeating itself. It's at the same place at x equals 3 as it is at x equals 11. And so the period would just be the difference between those two things. So 11 minus 3 is 8. And so we would say that the period of this function, which we're looking at the graph of right here, that period is equal to 8. So every 8 units of horizontal distance on this graph, my graph is doing exactly the same thing. And so another way to say that is any point on this graph at all, whatever f is at that point, I'm going to call it f of t, so t would be right here in this example. Whatever f of t is, that f of t is going to have the same value as this graph does 8 units later, f of t plus 8, right? Because t plus 8 would then be right here. So one way of using a formula to convey the periodicity of a function is to say something like f of t plus 8 is equal to f of t. And that this would then be true not just for a single value of t, like for example t equals 3. We can see directly that f of 3 is equal to f of 11. But if this is true for all values of t, that is what makes this truly a periodic function. It always repeats itself, no matter where it is at any time t, or any input value t. It's always in exactly the same place 8 units later, and therefore also 16 units later, 24 units later, 800 units later, 1,024 units later. Anything which is a multiple of 8 is going to continue to repeat itself. And now I'm catching myself. 1,024 is not, in fact, a multiple of 8. So let's go with 4,096. But you get the picture, right? Every 8 units, it repeats itself. And so 8 is what we would call the period of such a function. Amplitude is a measurement of how far vertically up and down a periodic function is exploring. So it's defined to be half the distance between the maximum value that my periodic function takes and the minimum value that my periodic function takes. And so in our example here of this graph, it looks like the maximum value that my periodic function takes is about 5, I want to say. So that's on the y-axis, right? My maximum value is 5. Minimum value that my periodic function takes in this example looks like it's 1. Okay? And so the amplitude is just half of the difference between the minimum and the maximum value. So 5 minus 1 divided by 2. The amplitude is 2. So that's how far away from that center line, the midline, my periodic graph ends up getting, both on the top side and on the bottom side, right? And therefore the midline, where the amplitude is half the difference between minimum and maximum, the midline is halfway between the two, and therefore is the same thing as the average. It's half of the sum of the max and the min. 5 plus 1 over 2. 5 plus 1 over 2, that's going to be 3. And so another way to say that is that this midline, this horizontal line, is the graph of the function, or of the equation y equals 3. So that tells me the center around which my periodic function is oscillating. It's half of the sum. It's the average of the maximum and the minimum value. So those are probably the three most important pieces of data about any periodic function. And the most important one of those three, I think, is the period. How long does it take for this function to repeat itself every time? And in the example of this graph, it takes exactly 8 units for this graph to repeat itself. So armed with that understanding of period, amplitude, and so forth, what I want to do is do 2 examples of sort of periodic functions and how we can think about graph transformations, thinking back to chapter 1 of our course, how graph transformations can help us to think about how period, amplitude, and midline are represented in a formula for a periodic function. So let's do that, again inspired by a problem coming out of Yoshiwara's functions modeling and graphs. So in this function, we're given kind of this funky looking graph. And the first thing that we ask ourselves is, how do we know that this is the graph of a periodic function? Well, we can kind of see this pattern that's repeating itself, right? We kind of have this funny looking M shape, and then it goes down, and then we have this little semicircle, and then it's again an M shape and a semicircle, an M shape and a semicircle. So this graph is just regularly repeating itself as we march along the x-axis in the positive direction, right? So this certainly looks as though it's the graph of some periodic function. So the first thing we're asked to do in this problem is just to state what's the period, what are the maximum and the minimum values, what's the midline of the graph of this particular periodic function. What I actually want to do is talk about the period last. Let's talk about the maximum and minimum values. Let's talk about the midline, because those questions are all questions about the output. These are questions about y values. And so to answer the questions about y values, what I'm asking is sort of how far up and down is this graph going. So the way I like to do that is just to draw in the horizontal lines that represent the maximum of my function and the minimum of my function. And answering the question about the minimum and the maximum first then is going to help us to answer the question about the midline and the amplitude. I'm going to actually add amplitude into this, even though the question doesn't ask for it. I also want amplitude. Okay, so what are the equations of the yellow lines that I just sketched in on this graph? They're horizontal lines, so they have equations that look like y equals a constant. Y equals something, y equals something. And all I'll do is just look on the y-axis to figure out what are the y-coordinates of the points that are on these yellow lines. Well, it looks like my one on top lies directly on the x-axis, so it has a y-coordinate of 0. And my one on the bottom has a y-coordinate, evidently, according to the axis marks over here, equal to -2. And so my maximum value for this periodic function is 0. My minimum value for this periodic function is -2. And so if I want to know the amplitude and the midline, I can find both of those things. Amplitude is half of the difference, max minus min, over 2. Right? And so it's 0 minus -2, all divided by 2. Do that out. I'm going to get 1. So the amplitude of this periodic function is 1. And the midline, instead of being half the difference, is half the sum. It's the average. So it's max plus min over 2. And so that's 0 plus -2 divided by 2. That's -1. Now what does that -1 correspond to? It corresponds to the y-coordinate of a horizontal line which goes directly down the middle of this function, halfway between the horizontal line representing the maximum and the horizontal line representing the minimum. Here's my midline, y equals -1. Right? Okay, so there's the maximum and minimum values, the amplitude, and the midline. What about the period? The period is the one where we have to look at the x values. How frequently does this function repeat itself? And so to figure that out, what we need to find are points that we know correspond to one another, points that are in the same part of what a mathematician would call the repeating unit, or the fundamental domain of this graph. So for example, what about the point right here, which is at the bottom of one of the sort of the M-shaped semicircles, right? That point occurs right here, but then another corresponding point occurs right there. So I'll mark that point also. And then it occurs again a while later, and so forth, right? So just mark a bunch of points that we know correspond to exactly the same spot in the repeating unit of this graph. Then we just have to measure the horizontal separation between those corresponding points to figure out how often this graph repeats itself. Right? So what are the x values of those points? Looking at the scale on these axes, it looks an awful lot like the x value here is 2, and the x value here is 8, and the x value over here is 14. And so if I want to know what the period is, I just want to know what is the horizontal distance or difference between these two corresponding points. And that difference is going to be nothing more than 8 minus 2, or 6. And so 6 is the period of this function. And sure enough, if I were to do that with this repetition over here, 14 minus 8 would also give me 6. So that gives me some reassurance that I must have done this right. We have some consistency in our measurement of the period. So the period is 6. The maximum and minimum values are 0 and negative 2, respectively. The midline is y equals negative 1, and the amplitude is 1 for this oscillation. So now what happens? Now we want to know what's going to change about this graph when I apply some graph transformations to it. And this is where things start to get good and interesting. Let's look at this first one. What does a graph of y equals 2 times f of x look like? Well, because I'm multiplying by 2 on the outside of my function, here on the right-hand side, what I'm ending up doing from a graph transformation perspective is I'm applying a vertical stretch of this graph by a factor of 2. So I'm pulling the whole graph away from the y-axis by a factor of 2. So every point is going to be twice as far away from the y-axis as it was before. And so y equals 2 times f of x is going to stretch away from the y-axis in a way that looks something like this. Oops. Let me try and get as accurate as I can get here. So my question to you is what's going to change about this function and the data that we have about this function, and what's not going to change? I keep screwing that part up. Down and then up and down and up here and down there, and okay, there we go. So here's a graph of what this would look like if I multiplied by 2 on the outside of f of x, right? I vertically stretch this thing out by a factor of 2. So what doesn't change is anything that we measured in the horizontal direction, namely the period. The period didn't change. The period is still 6. All right? This is still repeating itself every 6 units. But what did change are anything that we measured in the y direction could potentially have changed here. So the amplitude used to be 1. That may have changed now. The midline, which used to be y equals negative 1, now that's probably changed as well. The max and the min may have changed. Let's figure the max and the min out first, and then from there we'll use those to figure the amplitude and the midline. Well, my maximum used to be y equals 0. And if you notice, my maximum is still y equals 0. But my minimum, now it used to be y equals negative 2, but then we stretched that out by a factor of 2. My new minimum is y equals negative 4. And for that reason, my amplitude, which is half of the difference between these two, is going to have gone up by a factor of 2 also. The amplitude used to be 1. Now my new amplitude is 2. And the midline, which used to be y equals negative 1, is now y equals negative 1 times 2. Y equals negative 2. So when I stretched this graph vertically by a factor of 2, my max and min all got multiplied by a factor of 2. And for that reason, my amplitude and my midline also got multiplied by a factor of 2. Okay? So that's what tends to happen to a function when I apply a vertical stretch to it, a periodic function. Right? Okay. What about the second? I'm going to speed this up a little bit here. If I were to add 2 to my function instead of multiply by 2, so 2 plus f of x, right here. Now what's going to happen? Well, now I'm still doing something vertical because I'm operating on y values in this equation. I'm not operating on x values. But because I'm adding instead of multiplying, now this is a vertical shift. I'm shifting this graph up by 2 units. And so when I shift this graph up by 2 units, what I end up with is a graph that looks like this. Come down to here, down to there, up to there. Down to here, and then up to there. And so there is my graph of y equals 2 plus f of x. I've just nudged the whole graph up by 2 units. So what is the same and what has changed? Well, again, because we only did something vertical to this graph, the period, which is a horizontal measurement, that remains the same. My period is still 6. Let's look at what my max and my min were. My max and min. Now my max and min have both moved. Respectively, they used to be 0 and -2, but then I moved everything up by 2 units, and so my new max is +2, my new min is 0. And so when I take half of their sum and I look for the midline, 2 plus 0 divided by 2, my midline is now +1. So that midline has moved up by 2 units. It used to be y equals -1, now it's y equals +1. But the amplitude, because it's a measurement of distance, half the distance between the min and the max, 2 minus 0 divided by 2, that amplitude actually remains the same. So when I shift something vertically, I shift a periodic function vertically, I'm not changing its amplitude, which is the difference between the max and the min and the midline, but I am moving the midline itself, right, when I do a vertical shift. Let's tackle this last question. How can I change the graph of this function in a way that makes its period twice its original value? So I want to double the period. My original period was 6, right? And so what we're being asked to do here is to change this function in a way that makes the period of my new function equal to 12 instead of 6. How might I do that? Well, leaving as much else about this function the same. Well, remember the tools that we have in our graph transformation toolbox. We can do anything horizontal, anything vertical, and we have 3 different types of geometric transformations. We have shifts, we have stretches and compressions, and we have reflections. What kind of transformation from among those 6 possibilities are we going to be able to use to take this graph and change its period from 6 out to 12? Evidently, what we want is something horizontal, right? If I want to change the period, I'm changing a horizontal measurement about this graph. And so I need to be operating on the x's. But if I shift, if I just move the graph to the left or to the right, I'm actually not going to change the period, because the period is a measurement of the sort of intergraph distance in between corresponding points. And shifts don't change that, but stretches do. So what I need to do is I need to make points twice as far apart from each other horizontally as they used to be. I need a horizontal stretch by a factor of 2. That's the upshot of all this. Horizontal stretch by a factor of 2. That's how I'm going to change my period. So how do we do that? Using the formula for my original graph. My original graph is y equals f of x, right? How do I stretch that out horizontally by a factor of 2? I just have to operate on the x using either multiplication or division. And remember, when we operate on the x, we kind of go counter to our intuition. So if I want to stretch things out by a factor of 2, what I really want to do is I want to take the x-axis and I want to scrunch the x-axis in by a factor of 2. Shrink the x-axis so that the graph expands. That's what happens when we operate directly on a variable. So what I actually want to do is divide the x inside of my argument to my function. I'll divide that by 2. And that is how I'm going to get a horizontally stretched version of this graph. If I do that, what we'll see is a graph that's going to look something like this. And we'll go down to there, we'll go up to here, we'll go down to there, we'll go up to here, we'll go up to there. And so here's my new graph. F of the quantity x over 2. And just to reassure ourselves that our prediction was correct, let's take a look at these corresponding points on the graph. That's maybe at the top of my M right here. So where is the next one of those points? It's all the way over here. What is the difference between the x values here? This is x equals 14. This is x equals 2. And so sure enough, if I subtract those two, I get 12. And that 12 is going to be the period of my new graph. So we did what we were looking to do. So I think that's where we're going to have to leave things for today. We're out of time for this hour. And so, again, if you're in my course this semester, be looking for some quizzes to post on trigonometry, and particularly for the first quiz, quiz T1, is going to give you an opportunity to grapple with circular functions to help with this type of material that we were just talking about. And quiz T2 is going to be where you can flex your muscles on right triangles and inverse trigonometry, the couple of topics that were on my agenda, but we didn't quite make it to today. And so those are going to be where I pick up next week in our next session on Monday. I hope today's session was useful. I hope you're still doing good out there with the shelter-in-place order and everything we got going on. Not getting too stir crazy in your houses. I know I'm starting to miss campus a little bit. Maybe you are as well. But I hope you're doing great out there, and I look forward to seeing you more as we get into next week. Have a great weekend.